it's a little less trivial after I do the tracing out. But now I should specify what the initial state is. So the initial state, sort of in the spirit of the type of discussion I was doing earlier in terms of entropy and decoherence, I'm taking out my system and apparatus qubits and putting them in initial pure state. And then I'm putting the rest of my qubits in a quote-unquote thermal state. Note, because the whole thing is pure, this isn't, normally you would associate a thermal state with some mixed state, but really this thing is truly pure when you look at sort of how it's entangled. So the thermal state ends up being some state that's very entangled amongst itself. And maybe it's something I could just sort of leave as a comment for later discussion. There was sort of a lot of sensitivity, or there are certain choices of thermal states that sort of gave me the type of behavior I wanted and certain ones that didn't work. But I can maybe comment more on that later. But for now, this is just sort of the picture. This is your thermal-like environment, and you have a pure state. And then all you want to do is, you can think of it as I've sort of allowed, in some sense, it's like you've allowed these things to interact and equilibrate. Then you bring in your pure state system and now allow it to interact with everything else. So now it starts to entangle, get mixed up with the rest of them. And then ideally, if I've set things up nicely, you get something that looks like some sort of equilibration, at least from the viewpoint of these two qubits, meaning that they're going to go from some pure state to some higher entropy state, some very mixed state. I guess one last comment to be honest about these pictures. These look like a line of spins or something, but sort of when you reverse engineer what the Hamiltonian actually is, it would not sort of interact sort of locally like this. Sort of, there are a lot of very off-diagonal terms, so there's sort of qubits interacting with each other all over the place. So maybe lining up like this is a little dishonest, but just as a little cartoon. Yeah, so just summing up again, the full evolution is unitary. I specified the dynamics of the Hamiltonian. I specified the initial state, so and I know the recurrence time, so I could follow through the full evolution. And things like equilibration and fluctuations, and maybe this gets to some of the questions earlier, some of the concerns. Your whole system is sort of trivially evolving. I have some superposition of a bunch of different energy states. Their phases are just sort of oscillating sort of in the usual way. The full thing is staying pure. The entropy of the whole thing isn't changing. But it's once I trace things out that I start to see interesting behavior. I see things that look like fluctuations and equilibration. I don't really know when our end time is, but I'll just keep going. Is there a...
So
yeah.
What's the initial state of your environment, I guess?
Oh, the initial state of the environment. So this is a very entangled state. Maybe to use a buzzword that I ended up choosing, I chose a relatively high complexity state, measuring things in gate complexity. I'm not saying that is a key feature of the system. It just ended up being a particular choice in order to give me the type of behavior I describe later. So this, you can think, it's a very entangled state, and it's one that if I were to start writing down like elementary gates, like Adam was talking about in his talk yesterday, it would be fairly hard to undo it and get back to the 000 state.
But is it a pure state or is it a mixed state?
The whole thing is pure. Yes, all the reds put together is a pure state. So it's not really thermal like a mixed state, but it is. I want the entire system to be pure. Yes.
Could you describe the environment pure state as, just think of it as a Hamiltonian involving only 6 qubits, and just take the energy eigenstates of that with random phases?
Yes, I didn't. That's not how I created it, but I should be able to generate.
It should be typical of that kind of state, right?
Yes, dependent on what. So the actual choice I went with, it probably didn't evolve under the same sort of Hamiltonian, but that I would like that sort of interpretation in the end. This is sort of a typical state.
The Hamiltonian is very non-local, right? I mean, it acts on everything. So I think it's not clear what it means to just take the Hamiltonian for these 6 qubits.
Yeah.
Yes. Well, I didn't tell you what sort of Hamiltonian would thermalize this sort of thing. So I'm not claiming to give an explanation of how you sort of end up with this sort of state. That's sort of a separate discussion. How I would create that using some initial state and some other Hamiltonian. But yeah, so I haven't specified or really explored how I've set this up other than I just chose something. Okay, any other?
This is the fine-tuning problem.
Yes, well, we'll see. You can say this model is tuned in many ways, but maybe not. Well, let's get to some of the results. Okay, so here's what it looks like if I trace out everything except for one qubit. One of the qubits that was initially pure. So it starts at initially pure state. It starts with no entropy. And it very quickly approaches maximum entropy. And it has sort of, you might argue, like, does this really look like equilibration? I can sort of, I'll show a few other examples of states I've ended up with. But just at least in this one, you can sort of see there's sort of an equilibration-like behavior. If I made the system larger or sort of tweak the states and dynamics, I could have maybe had nice longer bits of equilibration time, or time spent in equilibrium. You have times that look like fluctuations. If it bothers you that these are sort of large, the initial ones, they're ones that are sort of a bit further away. But this, I think, at least I felt decently happy that this embodied a lot of the features I sort of wanted. I wanted to investigate, I wanted to compare, these large deviations where you'd have some low entropy initial states compared to these small little ones, which you think of being like Boltzmann brain fluctuations or something. Okay, so in a sense, I mean, you call this the initial state, but you could just as well call any other state the initial state, because this just repeats over and over. Well, actually, not quite this part. So the full recurrence time is 256. This actually takes you to the orthogonal state relative to that one. And then once you reach 128, you reach the same initial state as here. But anyway, this sort of thing just repeats over and over. So in some sense, there isn't really any beginning. This just goes through recurrences and repeats. So what I would like to think about is, does it look like decoherence is happening? I'm only going to focus on the one qubit system. I'm not going to do the sort of splitting into system, apparatus, and environment. Oh, and just a brief look at just to throw up a few other states. I'm not looking at as long a time scale, but you see you can get sort of different looking sort of oscillations and things. And for a lot of choices I tried, I ended up with the entropy of the little system just wanted to oscillate. And this is probably just due to a bad choice, but it's something I would like to think about a little bit more. So going back to, this is referring back to the first entropy plot, zooming in on the very beginning, looking at the first very large change in entropy. You can see the entropy here. There's sort of a little bump here where the entropy drops again. I think with tuning the choice of state and environment, I can tweak that. But regardless, I can now try to see, does it look like decoherence is happening? So I tried different choice. I diagonalized at different times and tried to look for a pointer basis. And this was sort of one of the best examples, focusing on this time, where it looked like, with the exception of this sort of recoherence popping up, this looked like it sort of, at least on a surface level as a first look, looks like sort of the decoherence story is happening. As the entropy is growing, the off diagonals are dying off in the pointer basis, and it looks like you have potentially some classical description. Maybe as I refine the model further, you can say there was a initially quantum type of measurement that then you can describe classically. Now, to get to talking about the smaller types of fluctuations, there's some interesting things I have noticed and can talk about, but I still don't completely understand them. So here's sort of zooming in on the two later little fluctuation type things where you pop down from nearly maximal entropy. After searching for a good pointer basis for these, I searched for them independently, but this This was one example that seems sort of decent for the other ones, or for both. This one sort of looks like it always sort of stayed approximately diagonal, although you have to be sort of mindful of how much do I care about the amplitude of these apparent oscillations in the off-diagonal term. And this one, it seems like there's possibly some difficulty in keeping a decohered picture, despite there being not significant changes in the entropy. You sort of get these oscillations in the off-diagonal term, suggesting, and this was true, you get even worse than this for other choices, which I'll show you one other one in a second. It seemed like there was sort of a reluctance to decohere here, which is something I would like to understand more. But at least this is a start to adding something to say to this picture that the entropy itself does not tell you. Because remember, the entropy doesn't tell you everything. It doesn't tell you the whole story. It's just telling you, in essence, something about all the, some combination of all the eigenvalues of the density matrix. So it doesn't necessarily tell you when you have this particular downtick in entropy, what is going on a more fine-grained level.
So how do you look for a pointer basis?
So this is just sort of a dumb search where all I do is I take states at various times and diagonalize, and then use those as the pointer basis, and then look at the off diagonals in that basis.
I mean, so at every point the state will be diagonal on a different basis.
Yes.
So kind of, in some sense, you should try all possible bases. I mean, you could make the epsilon 1 for every possible basis.
Yes.
And it will probably look very different. Right?
Yes, it looks very different. But in other cases, like maybe this is a little bit. If you want to say decoherence is happening, you expect the off diagonals to be dying off, sort of like towards the end, as you sort of expect. So I'm mostly interested in what's happening near these fluctuations. So.
Must there always be a pointer basis?
Well, I guess I would say not necessarily. I mean, I'd say this is, so I haven't shown you the complete exploration around this area, but exploring all the data points and diagonalizing around these fluctuations, you see things like this, and you see worse. Like, it'll hit 0 wherever I happen to say. So if I just followed it, like if I picked like this point and I diagonalized, it would hit 0 there, but then it might look sort of, really bad elsewhere. There'll be other places where it'll drop down to 0, and this is sort of adding to the story that because if it ever becomes maximally mixed, it'll look, it'll sort of become degenerate, and different bases will start to look nice when I describe it. But yeah, question?
So yeah, actually, couldn't one actually diagonalize at each time and just somehow follow this frame, how this frame itself is evolving, the diagonal, the main.
Sure, that's another way I could.
That's the way I showed it on Monday.
Oh.
Yeah, so this is just sort of some initial look and evidence for whether it's diagonalizing or not. Yeah, I could instead keep track of like what directions or the pointer basis vectors are pointing in, or I could just keep track of one because there's just 2 in this case. But yeah, I could keep track of.
There's something stabilizing.
Yes, right. But I guess just going off of this for a little bit longer, I want to comment this. So this red plot, this is using the, and I apologize for changing colors from 2 slides ago. This is looking in the, what appears to be the pointer basis from the initial large entropy change. You'll see that it behaves noticeably differently, and from having looked at different points, this seems like evidence that different fluctuations are favoring different pointer bases. In particular, It does not look as nice sort of around here, and you can see sort of a different description looking near this fluctuation. So it's something I still want to explore more. It's a good idea to try to track, for example, which way the pointer basis vector would be pointing. That's a good idea. But yeah, this is just sort of a first look and part of some early ongoing work trying to understand, at least in this simple toy context, toy model context, proof of concept, what's happening in terms of decoherence. So maybe I don't really know when the time is running up, but I guess I'll start finishing here. Right, I sort of said the first point, the evolution of the off-diagonals I think is suggesting to me that maybe there's something sort of interesting happening in terms of whether or not you are stabilizing on some pointer basis. I need to do more analysis, and I also want to explore more initial states and a wider range of things, and I want to eventually sort of construct this in such a way where you can see the type of interaction happening on a certain time scale, where you see the system environment entangling in such a way to do like a measurement, which then later decoheres with the environment.